Hello, everyone, and welcome to today's webinar. My name is Khalil Doheny. I'm head of content at Digital Niche Agency. Today, I have Charles, CEO of AtomBeam, and then AtomBeam advisor, Greg. How are you guys doing today?
Good, good.
Great.
How are you, Khalil?
Doing awesome, doing awesome. And, I want to thank everyone for attending today. I know it's a Friday towards the end of the week. So, everyone's getting ready to check out. So I do appreciate everyone taking the time out of your days to tune in. Before we jump in, Charles, do you want to give a quick background of yourself and introduce Greg and the whole purpose of today's webinar?
Sure. Yeah. No, thanks, Khalil. So today, one thing I talked about previously and also posted about and so forth is sort of like, how does this compaction really scale? I mean, how does it turn into something that's a really cool thing that you can add in here with some engineering work and stuff into something that is in everything? Because I think a lot of, probably most of the people that tune in here understand that this could be a huge thing. It could be how every machine talks to every other machine, but how do you actually do that? And it's not by, somebody sitting there on their iPhone doing some command line engineering. It's going to be something that's totally automatic that you don't even know is happening. So the manifestation of that, how does that really happen? That's what this is about. And so I've asked my friend and classmate from business school, and also a guy who's run venture-backed companies that make this kind of thing happen, whose name is Greg Caltabiano, to join us on this call. And he can explain kind of like, not sort of like, he's not going to dig into the engineering in a deep way. He's mainly going to talk about, here's how it works, here's how the industry works, and here's how this really could evolve. And that's the kind of thing that he's understood and run companies about and so forth. So Greg, do you want to talk a little more about your background and all that, if you would, please?
Sure. So great. It's great to be here and to be able to talk to everybody. So my background is, I have a technical background, but mostly in management. And I've been in wireless, in networking for 30, 40 years. And I've worked with electronics and software and taking very advanced technology and turning it into consumable, low-cost solutions. And this is using hardware, software, combination of the two. And in particular, the companies that I've run have been companies that have had to take an idea and bring it through this product development stages to become more and more high volume. And that's what we're going to talk about today.
Right. So thanks, Greg. That's great. So without further ado, unless Khalil, you have something else you want to say.
Yeah, just quickly, we're going to have a presentation that Charles is going to be sharing. And throughout that presentation, if you have a question that you'd like Charles or Greg to answer, please leave it in the Q&A box below. We're going to have some time towards the end, but if we feel like it's right to ask it throughout the presentation, we will as well. So if you have a question, please ask it in the drop box.
Right. All right. Thanks. Okay. So without any more chatting, we'll get going here and start this rolling. Okay. So as we said, this is about where the product can go from here. And to that end, what I want to do is sort of give a quick primer on reminding everybody how this works. What do we do? So first, we build a codebook, and that's done by looking at a big data set and taking the patterns in the payload of those messages and breaking them up into patterns. And then we use machine learning to look in those payload patterns for repetitions of pattern that we see a lot. They take those patterns, and we put them in a code book, and we match up each pattern with a code word. So you might have a 128-bit pattern that we see a lot, represented by a 3, 4, 5 bit code word. So that's sort of the magic here. It's turning these, making a representation of something 64 bits or 128 or whatever into something that's 3, 4, 5, 10 bits long. And that's really how this works. And so you say, okay, when do you do that? Where do you look for the patterns? That's a big difference between this and compaction and compression. Compression is doing it in live data. It's looking for the patterns in live data, which is slow and heavier computing. What we're doing is instead, we're dividing it up and looking for those patterns in advance. And that's what we do to build these code books. And so once you've done that, you can do a runtime encoding. And so all we're doing here in runtime is we're taking that payload of a given new file, cutting it up into patterns, matching the patterns to patterns in the code book. And then we take the code words that we find and we pack those into a file that's just the header and the code words. And then in live data, you have code words, code books on both sides. And all they're doing is talking to each other using the code words. So the data itself never goes anywhere. It just sits there, and all you're going to do is build these code books, put them in both sides. And then in runtime, you're doing one of the lightest things you can do in a computing sense. You're doing a lookup. You're just matching this to that. So it happens in microseconds, which is super fast. So anyway, that's the magic of this thing. And because of that, you can do two things. One, you can effectively, on average, and it varies, but on average, you can send 4 times more information than you could before over the same pipe, over the same connection. And the second thing is you're obscuring what that data is, because what you see is in these code words is gobbledygook unless you're the computer and you have the code book. So what that means in effect is you're looking at, here's a file, that's a real file. And then when you compact it, you get this, which is the same information, all the same information, but you can't read it, right? It's all encoded stuff. And the only way you're going to read it is if you have a code book, or you have some pretty big heavy iron in terms of being able to to be able to decode what this means. And if you do, though, if you have that code book, it's just like you're reading the original data. And so it's pretty cool because it's both security and it's reduction in the size dramatically on a real-time basis. And it's amazing how significant this is, given how much data moves from machine to machine. So it looks like we have a question. Is that something at this point, Khalil, or?
No, we can
okay.
Come back to that one.
Okay, so that's just the quick reminder primer on compaction. So what I'm going to do now is we'll move into, well, that's right, I wanted to differentiate too, I forgot this, but basically, so I want to emphasize there's 2 things that happen when we do this. One is what happens when you're building the code books. And that is a completely separate thing than what you do in live data. So build the code books, you got a bunch of samples, little messages, thousands of them, millions, and you build the code books using those. And then once that's built, whole different thing is the runtime. And you may or may not have the capability to build a code book in something, but you always are going to have the live data. Here's the communication actually happening. That's what I'm here to talk about, and I'm going to be turning it over to Greg. Do we have anything we want to address first?
Yeah, we have a couple questions here.
Okay.
How is excuse me, how is this different than the Riverband technology has been doing since 2002 with their WAN optimization? Have you verified that this doesn't infringe on existing patents?
Yeah, that's a good question. Yeah. So yeah, we have looked at Riverbed, and we had some pretty, some experts who used to work at Riverbed look at our approach and theirs, and there are some pretty significant differences. One of the key ones is that and I'm trying to remember because this was a while ago, but a lot of it is based on sort of like, yeah, okay, just the idea of having a small thing representing a big thing is not unusual, new, been done before for sure. And that's kind of where a lot of the relationship ends, but the building of the code books, the way we do it, the sizes of what they're talking about, they're working in very big things. They could not operate their stuff on, for example, a really small little sensor or something like we can. In terms of like, I'm trying to remember because we did a pretty close analysis to make sure that we were not in any sense infringing. It has been looked at. I can't give you all the details right off the top of my head because that was a while ago. But there are some really fundamental differences between what we do and what they do. But clearly, we do share the characteristic that you're building something that involves a small thing representing a big thing. But beyond that, there isn't that much that's the same.
Yeah, and then we have another question. This one's for Greg. How did you hear about and get involved in AtomBeam? What was your initial reaction to the tech?
Yeah, Greg, please.
Sure. Well, Charles and I have known each other for a long time. So from the beginning, he talked about what they were doing. And I recognize that this is an incredibly pervasive problem that's getting worse and worse. And that is there's more and more data being sent across all different types of networks. The amount of data is increasing a lot. And also the other thing that I saw is the type of data is, there's lots of different types of data. There's data that's variable size packets and small packets. It's a lot of IoT data. And then there's video, which is in a different category. And there were all sorts of solutions that had been attempted and relatively successfully for video. But the whole other area of smaller packets and variable packets was a problem that others hadn't solved that well. And second, I saw that the AI revolution, all these new techniques, new approaches, new ways of looking at problems was really an opportunity to relook at some of these issues. And I saw what Charles and his team were doing, and I got very excited. So yeah. I wanted to, any way that I could help, I was, very happy to do that.
Yeah, he's been super helpful. We involved him early. He has a great perspective. He serves on boards of significant companies. He sees, kind of like the bigger picture and sees where this, and that, right, he got pretty excited about it when he first started looking at it, and he understood it and the implications very well. Greg has been a super big help for me in particular, but generally for the company.
There aren't any other questions at this time, so if you wanted to continue.
Okay. All right, great. So without further ado, Greg, do you want to start your chat here, please.
Sure. So what I'm going to mostly focus on, I'm not going to talk about the specific technology of the compaction, of what AtomBeam does, but I'm going to talk about how do you turn this technology, how do you instantiate it? How do you turn it into something that the customers can consume in a way that they're used to consuming it at the price points that they consume it? How do you turn this technology into a business, essentially, into a scalable, large business? That's what I'm really going to focus on. And today, there's software that does this technology. That software is integrated into the software of what the customer does. And that works, but that's not ideal because the customer then has to do work. And what I've seen with technologies like this that really scale is you have to make it simpler and simpler and simpler for the customer to use it. So the customer essentially has to do almost nothing, and then they get the advantages of this. Because the model for the company is to be as pervasive as possible, because the problem is everywhere, that data needs to be sent more and more efficiently, less and less cost. The types and potential variety of potential users is huge. So we looked at, okay, how is it being done today? And how does this evolve into the future to make this usable by everybody? And we looked at lots of different industries, and they all kind of follow the same path. And that is, they start out with software that says, okay, let's make sure it works. Let's try some proof of concepts. Then you want to make it even broader. And then you say, okay, rather than the customers needing to integrate this into their existing stack, what if you could put it into a little simple industrial, very tiny PC, or equivalent of a very tiny PC, basically a little processor on a board or in a box. And so that in that case, the customer just needs to plug it in, data comes in, data comes out, very simple. And that would work for relatively small customers, but they're able to use it quickly, they're able to validate it. And the business case is so good in certain use cases where bandwidth is a little more scarce or more expensive, that this will actually turn into some revenue. So it gives you revenue, it gives you experience, it allows you to continue to tweak your algorithms to make it more efficient. Now, as Charles and the team have been talking to other customers, there's a whole class of customers, military, aerospace, big industrial. And what they want is something a little more hardened, a little more, to have a little better ratio of power to, to cost and to size, things like that. So the next step in this evolution is to what's called an FPGA. And I'm sure in the audience, there are those that are possibly experts in FPGA, and there are others that probably have never heard of it. Basically, what an FPGA is taking logic. So you have an algorithm that does something, and you could put it into circuits, but by putting it into circuits, then yes, it's very efficient, but once you put it into a circuit, it's hard to change. An FPGA is kind of a cross between software and hardware. You program an FPGA to do particular algorithms, but it's implemented in some flexible hardware. That's really what an FPGA is. And the advantage of FPGAs is, one is you can change it with software, you can keep changing it. But the second advantage is it's smaller, it's denser, and it's much more cost effective than using, say, a computer that has the same type of power. And so applications like military, aerospace, industrial, they often use FPGAs. FPGA, each of these steps, both the software, which is the first step here, the industrial mil-spec dongle and gateway, as well as the FPGA, are both a stage to get a greater sector of customers to actually incorporate this, as well as a development path. So as these customers use it in these two stages, and there's tweaks or changes or suggestions or even improvements, they can be done without changing hardware. They can be done by uploading new software. And that's the real advantage of this. But if we look at the end game and we say, okay, what is the final step here? We need to look at other similar types of functions that are ubiquitous. And one of the kind of the most obvious examples is something like cryptography. You know, there's cryptographic functions that are in many, many different systems. And those are done in hardware. They're done inside chips, usually now. There's other types of coding. There's other types of functions like this. And what is done then is the FPGA, which proves to you that this actually works, it proves to your customers it's actually worked, can be converted to basically hard-coded, to basically circuits. And those circuits, rather than having to do a chip just to do this, because that would be overkill, actually becomes what we call IP, which is a functional block that goes into other people's chips. A great example of this, let me give some examples. By far, the best example is ARM. Many of you have heard of ARM. ARM is the most widely used processor in the world. And when I say widely used, we're talking about probably 100 billion processors a year. So it's not just cell phones and iPads and all of this. It's just about everything other than PCs. And ARM doesn't make any chips. They don't make any hardware. What they do is they license what we call an IP block, which is software that you put, or it's a code that you put inside your ASIC, which is a special purpose chip or any chip, and it turns into circuits when you make it. So if you want to do a routing chip that has a processor in it, you don't design your own processor, you just license it from ARM. So in the future, what I see with AtomBeam is if someone wants to have this compaction to get much, much more efficient data transmission, they would just license it from AtomBeam, very small, inexpensive core that would become part of their chip. And the business model is that AtomBeam would get a license fee for every chip that's sold, exactly what ARM does. So that becomes the model. It's a step-by-step process. So as you go to the right here in this slide, it takes more development resources for AtomBeam to develop it, but the unit cost for the customer is very, very low. And when I mean low, we're talking about cents or tens of cents when you're all the way to the right. So it becomes a very easy decision for someone who's designing a chip or designing a system.
Great.
We have a question that came in. What are the cost differences to the user between the three formats of dongle, FPGA, and ASIC?
Well, I can give you orders of magnitude. I think that may be better because rather than the exact cost. So if we start all the way on the left and say, okay, what would these small form factor computers cost? You know, Charles, you probably have the best idea since you're using them.
Maybe $100.
Yeah, $100. An FPGA is, for those of you who have bought FPGAs, they go all the way from $10,000 down to $20, $15, $20, depending on the size. The amount of processing that needs to go on here is relatively low. So I would say, you know, you're talking about $10, $20, $25 roughly at the most. Then when you go to an ASIC, the incremental cost of this functionality is cents. It's 5, 10, 15, 20 cents, depending on the volumes. So you can see how it changes drastically as you go down the curve here. And you want to make it economically a no-brainer for your customers. You know, for that type of price, with the type of efficiency gains that Charles is talking about, you don't even think, you just do it. And that's what causes ubiquity. That's what causes everybody to put that in their chip.
Awesome. And I just did want to reiterate, we will not be taking live questions. So if you have your hand raised, we will not be taking those. If you have a question, please ask us in the chat box below. Thank you.
The Q&A box, you mean? Yeah, right. Great.
Yeah.
Whatever. Doesn't matter. Okay. All right. So fire away.
Yeah, so we talked a little bit about this, but at this stage, when we're talking about small form factor computers and gateways, servers, it's basically running in software, either in its own computer like an SBC or incorporated into the server software. So this is kind of where we are today, and working through this step right now.
Yeah.
And there'll be some customers that can use this in production, but it'll be small volume.
Right. And the emphasis here at this stage is moving it from, you have to do some engineering to get it working in a given box, to it's really way more, it's very automatic within the set of constraints of, it's an ARM-based device and it's using a version of Linux or whatever. And so long as we have those basic parameters being true, all you really need to do, all we have as a focus right now is making all that as automated. You don't have to mess with it. There's no engineering. That's the idea of this stage. And that's what we would call productization or autonomy at this stage of taking what we do now, which requires some engineering, not very much, it's purely, you just buy the box and it's there and it's all set and ready.
Great. So let's talk a little bit more about FPGAs. So when I was running a chip company and we would do a design for semiconductors, we would always try out the design with an FPGA first. So we would do the coding for the circuit. It's not software, it's coding for the circuits. He was using a different language called Verilog. But in order to ensure that it worked, we would first do it in an FPGA, which would replicate how it works, do all sorts of testing on it, even give it to customers to test it. And then once we knew, okay, we've tested it, our customers tested it, it really works, then we would go the next stage to put it into an ASIC or put it into an IP block. The reason I'm bringing that up is when you look at the 3 stages in the previous slide, where you go from software to FPGA to ASIC, if you didn't even want to do the first 2 stages, or if you weren't going to productize it and sell it, you would still do those stages in order to ensure your final stage is successful. Because when you do an ASIC, you don't want to make mistakes. You're doing circuits, it costs you a lot, and to make changes is expensive. The beauty of this path, though, for AtomBeam is not only are these stages along the development that de-risk the development as things are tested both internally and with customers in a wide variety of sectors. So not only is it testing, every stage of the way you can start to get revenue, because there'll be a set of customers where the form and fit and size and cost are good enough for their application, and have enough of a urgency to use it, where they can actually use that stage. I mean, a good example is military. The military is not going to wait forever for this. There's certain applications that are so important that they may take an earlier stage, say an FPGA, and feel very comfortable with it, which is they often do with some of these types of technologies.
Yet it might even be preferred in some circumstances, right? Because you can reprogram it.
Yeah, exactly. They may prefer it because they may decide, we'd like to do this, but we want to leave open the possibility that we can change it in the future without a lot of pain, and we can do it quickly. And that's another benefit of these FPGAs. And the FPGA hardware is standard. It's not, the hardware itself is not something that AtomBeam has to do themselves. They buy it off the shelf. There's many vendors, very well tried and tested in the industry.
Right. And, and just to emphasize here that this step is what, we proposed to the Air Force in a first stage, in conjunction with an outfit that does the kind of development work that we're talking about moves a software that works on a regular processor into really fundamentally, it's really rewriting it in a different language, and thinking through all of the logic of it. And that is not a light lift, but at the same time, you need the kind of specialized help. It's not something a software company like us would undertake by themselves unless we hired people who specialized in doing that.
Right. Okay. So this slide kind of explains a little bit what we talked about in the last slide. You know, basically what we're talking about is the type of work at every stage. When it's pure software, the stage right now, you can work on the algorithm, you can tweak it, you can make sure that it works with lots of different types of data, and work out exactly how this is going to work in the future. Then when you go to an FPGA, as Charles mentioned, there's a little bit of what we call refactoring, which is looking at the algorithms, looking at the code and saying, okay, how would we do this with this different language called Verilog in a slightly different partitioned way so that it works really efficiently on an FPGA. And you want to do it on the smallest FPGA that will work, because then it's the cheapest and lowest power.
And least difficult to get into whatever it is you want to put it in.
Right. It's just cheaper, lower power, smaller form factor, you know, but off the shelf, definitely off the shelf.
Right.
And it's well accepted as that those FPGAs actually go into production. They're not just used in the lab. And also at this stage, you can do lots of testing. Customers can test it. AtomBeam can test it internally. And if there's a problem, you can fix it very easily. And that's really what we show in this next stage, is in these leading edge applications where the customer says, you know, 4-to-1 decrease in the amount of data I need to send to be able to send the same information is so big, it will be so effective for me that let's go as fast as possible. I'm willing to start with an FPGA, definitely. Let's get it into our equipment so we can start testing it.
Right.
And this makes it very easy to do that.
Right. And it does sort of speak to who are your early targets. And it's not putting an ASIC into a refrigerator, so it's sending it over your Wi-Fi, a little less data and stuff. It's sending it from an aircraft that has limited bandwidth that needs to get more data to the ground, or it's somebody sending data over a satellite that is costing them $1,000 a month to send, that you can make $250 a month, or that sort of thing. Those are the targets for the early days stuff, because as Greg was saying, it's very clear when you talk to people. Like, I was just at a satellite conference this week, and you talk to people, some of them are desperate to figure out how they can reduce the amount of data. Whereas, again, if you're talking to somebody it's a convenience, it's helpful, sure, I'd do it if it was there and it was cheap, that's when you talk to them about the later stage, putting it on an ASIC kind of thing.
Yeah. I just want to emphasize something. Many people think that in our world now with 5G and the internet and fiber, that bandwidth is free. And in certain, and I think the truth of the matter is there are certain places where bandwidth is not a constraint, but there are still many, many places where bandwidth is very constrained, or where channels, wireless channels, are so noisy that you have to do a lot of, for example, error correction. So you have to send a lot of extra bits that don't really pass information, but make sure that you have a viable channel, or cryptography or things like that. A lot of this is military, aerospace, more rugged applications. Satellite is a great example because the satellite channel is limited. There's only so much you can get through so much frequency. So yeah, right. So therefore, these are the ones that will be the earlier adopters. These are the ones that will go, I think, with FPGAs in many, many cases. And then later, the ones that say, you know, if I could reduce my the amount of data that I'm sending and not lose any information, and it doesn't cost me much, of course I would do it. Why wouldn't I do it? And those are the targets for the ASIC. And those, once you do that, it's basically everywhere, because almost everything we do involves sending data.
We have a question here from Bob. How long do these 3 phases of development generally last? And how long does the testing on the FPGA last?
Well, let's kind of break it into pieces here. So, the thing about development with this type of thing is that developments are actually relatively quick and the testing is relatively long. And the testing is both internal, but the customers, depending on who they are, may use it, may test it and use it for a while. For example, if you look at the military, they're not just going to take it and then throw it into a missile. They're going to do a lot of testing on it. And it's also true for some of the other applications here: construction equipment, oil wells, and transportation. So a lot of the timeline for testing is often driven by the customer, and what does it take for them to feel comfortable. So, and Charles, you may have a better idea on some of these applications, how long they would test it.
Yeah. I would say, just to try to put, some amounts of time down, I would say that a lot of it is driven by how much money you got, right? But let's just say we have all the money we need as we go along, which is a big assumption. But let's say we do. I think probably putting it into an FPGA, I would guess in the range of 9 months-ish, something like that. Does that sound reasonable, Greg?
Yeah, absolutely. Yeah. And then the question is, how long will customers test it? And that will depend on the customer.
Yeah. And, and plus, a number of customers testing it in various things.
Absolutely.
That might be anywhere from maybe 6 months or something like that. And not only that, you're not even just customer testing, you're also doing automated testing. It's putting it on a computer and banging away with all sorts of things, that making sure that you've tried everything possible to break it, and then correcting it. So part of what the time frame would be involved is how breakable is it, and how much do you have to do to fix things and make sure that you don't have any bugs whatsoever, etc. And so, it's hard to put an exact amount of time on it, but it's maybe 6 months or something before you could really undertake a process of moving it into ASIC IP core, saying, okay, I'm ready to lock this in and put it into hard code, and so into a circuit, as Greg puts it, so that, I'm ready to really commit. And the issue there is you're writing big checks, and so you've got to be sure that you've thought that you've done everything you can to make sure that it's not going to break.
Yeah. But one of the beauties of this approach, though, is the things you do to de-risk the ASIC IP is you have the FPGA, you have a lot of customers using it, they're testing it, you're doing the automated testing that Charles talked about. So all of that stuff gets you to the point where once it's really ready to go with the FPGA, and you really have stopped bugs, bugs are not coming in anymore, and you really believe you have the right functionality in there, it's very fast to turn that into a circuit. It's almost an automatic process. Now, there's some other steps that you take, but that can be relatively fast. But you also have the process of hardening, what they call hardening the IP, making sure that the same block can work in many different chips. But that's probably another year to 18-month process, but not longer than that at that point in time. But only at the point in time where you've been through the FPGA stage. Otherwise, it's much longer.
Right. And the FPGA stage is like Greg is saying, it's one thing to do it, to code it into an FPGA. It's another to make sure that you've tested it in every way you can possibly do.
Yeah.
Because people will come up with things that, pretty hard to think of in terms of overloading it, trying some weird data, doing something. So you got to be sure. That being said, I think we've done a pretty good job at this stage to, stamp down bugs, but are we ready for FPGA? Or are we ready to put it in ASIC? Not even close. So the point here is, as Greg is saying, is it's really about the testing at least as much and probably more than the actual coding it into an FPGA. It's being certain that that is really rock solid. Okay.
Okay, so let's talk a little more. I mentioned this before, but let's talk a little more about how this works. So I'm a chip designer for XYZ company, and I'm doing a chip that, let's say, goes into a piece of factory equipment, and this factory equipment sends back pictures of inspection pictures of what's going down the line. Right. So I'm sending a decent amount of data, and I'm spending all sorts of telemetry data that's saying, okay, this is the temperature, this is the humidity, there's no vibration. So you're constantly sending all this data back to some server. And I want to put an ASIC in this equipment so that I can have it, relatively small size. So what would I do? The first thing you do when you design a chip is you say, what are the basic functions that need to be there? I need a processor. I need to get data on and off the chip. Maybe I need to do this compaction. You decide what you need. You figure out what can you get off the shelf as far as functionality. So you want to do as little design as possible when you're a chip designer. Otherwise, it takes you forever. So I'll take the processors from ARM. I'll take the compaction from AtomBeam. I'll take the digital signal processing from maybe a company like Siva. And then the only design I need to do is to stitch it together with circuitry, which is a lot less time. And then, as all of these things, I need to do a lot of testing. But since each of these IP blocks has been so well tested, in essence, what you're testing is the interconnection between the two. And that's really how chip design happens today. And this is how remember, ARM is one of the most profitable, highly valued technology companies out there. Everybody's dependent on them. It's because they're so easy to use. And yet they don't make anything. They just license IP that goes into other people's chips. And even Apple, with all their money and all their engineers, when they design their own chip, the M1, the M2 that's going into everything, guess what's inside it? An ARM IP license.
Right. And, to emphasize here, or actually, why don't you speak to like how ubiquitous ASIC, and we're going to talk IP core also, how ubiquitous those are in whatever device you happen to have in your hand, your phone, your modem, your router, your garage door opener, whatever.
Yeah, it's hard to imagine how many things you have in your home and in your car and in your office that have ASICs. It's such a huge number. It may be, maybe in a car there may be maybe hundreds of ASICs in one car. In in the home, there's probably even more. Every piece of equipment you have, everything you buy now has ASICs in it. And most of those ASICs have processors, and more of them send data either to the internet, to Bluetooth, to Wi-Fi, or even between different chips and parts of the same equipment. And all of that benefits from being able to send less bits, but send the same amount of information.
And talk about, with ASICs, like how, all right, now this says application specific. So can you put more than one application in a application specific chip?
Well, what application-specific circuits, which is ASIC, means is that you have a particular thing you want to do, like manage a refrigerator or manage the ignition system in your car, or do some of the special processing you need in a cell phone. And so that is a specific set of functions that you want, as opposed to the opposite of this would be something like buying an Intel processor, which is just some standard processor, and then you process it. You put software in there to try to do what you want, but it may not have specific blocks that you need outside of the processor and what you can do in software. So what's happened is it's become so much more cost effective for companies to do ASICs to do particular functions than it is just to buy processors off the shelf from companies like Intel and just program it and then put discrete components on circuit boards. So it's become such a well-established thing, probably for the last 25 years. You know, it's been really going on for quite some time. And the reason is that if you're going to make a lot of them, the costs for each ASIC could be very, very low. So it really drastically reduces the cost of the equipment, but doesn't, you don't lose functionality. In fact, you can gain functionality. So that's the basic concept.
Right. So, yeah. So give us some hard examples of like what you might find in an ASIC doing.
Sure. Well, let's look at a good example is an ASIC that is in your home router. Okay, because there's definitely an ASIC there, at least one. That ASIC will take there'll be a circuit that a wire essentially that comes into that ASIC with data coming along it. Okay. Now, to get into the ASIC, there'll be what's called a SerDes, which turns the physical the physical pulses on that circuit into bits, logical bits. So that's one piece of IP that does that. Those logical bits will come in and they will be categorized and packed, and the headers will be read, things like that. That may be a separate piece of IP or circuitry in there. There'll be a processor in there on that ASIC that maybe will do some of the managerial functions like different configurations and settings. There may be IP from memory. Memory is an IP often on an ASIC. So rather than you designing your own memory circuits, which nobody does anymore, you'll off the shelf get some IP, license some IP, and you'll put a little bit of memory in there because maybe you'll have buffering for the packets that come in. So, one chip could have 10 or more pieces of IP that go into your ASIC. And if you didn't have this off the shelf IP, you'd have to design everything from scratch. It would take forever. It would be much more error prone, much less efficient. But just as in software, you don't do everything from scratch. You use off the shelf operating systems, off the shelf compilers, et cetera, et cetera. In the world of chips, it's even more so. You take everything off the shelf you can get, and then you design the interactions between them in the circuits. So this would just be one more thing that goes into the catalog. And then makes it very easy to use. And it means that every customer, that you don't need to customize for the customer. They just take the IP block as it is. They drop it in. They know how to do the interfaces because that's published as part of their license, and it works.
Right. Khalil, you look like you have a question. I think you're muted.
Yeah, no questions as of now.
Oh, okay. All right. I thought I saw something pop up. Okay. All right.
Yeah. And then I already kind of talked about this as the IP blocks. I think that people who are not in the chip industry don't realize the extent to which we just depend on these IP blocks. The entire semiconductor industry would work a lot less efficiently. It would be like we were 15 years ago without the ability to pull things off the shelf. Right. And build on what other people have done.
Right. With a cheap little added license. Right.
Yeah, it's just a license and it goes into your chip design software and pop, that functions comes.
Great.
And I just, again, we talked about why am I involved in this? What got me excited? I just see this as a universal problem that's going to get worse and worse and worse. We will never be able to send data as efficiently as we like. We'll never be able to make it as the transmission as cheap as we like. So every time we have improvements in this, there's huge value to a very wide set of customers.
You might talk a little about how it's not just sending the data from and to the computer, but the logic board connections.
Yeah, I think, if let's look at a data center. Here's a good example. A Google data center or a Facebook, a Meta, or a Amazon data center. If you go into the data center, they have tens of thousands, hundreds of thousands of processors in there, of computers, basically servers. And they have lots and lots of memory. But more and more, the limitation is getting data from one server to another server. Because in a given, if you do a search, there may be hundreds of servers that have some element of the computation that goes into your search. And this works in some choreographed way that's pretty amazing. But as more and more processing power is added and more memory is added, and processing power and memory is getting cheaper and cheaper, you still have to get the data from one server to another. So you have faster and faster interconnect, which costs more and more money. And that's, of course, one way it's going. But if you could say, okay, we want to send this data, we don't want any loss. Is there any way we could actually send less bits, but at the other end, kind of unpack it and have the same amount of information? And as this becomes cheaper, as this, for example, becomes a standard IP core on their server processors, for example, or on their networking processors, then it's as though you're getting 4 times faster wires. But you're not. You don't need to. You're just getting the data as though you had 4 times faster wires. So that's why this is an incredibly pervasive problem in data centers. And of course, it's even a bigger problem earlier in things like satellites and wireless, where bandwidth is even more constrained. But it's such a universal problem that I just think it will become very widely adopted. And that is why the end game is an IP block, because you need it to be, the unit cost to be so low that it's a very easy decision for someone just to put it into their processor chip or networking chip or memory management chip or something like that.
At what point along the product development journey would it be necessary to raise funds through a Series A, for instance, or can government/private contracts fund the process entirely?
I mean, I'll try to tackle that. I'm happy to have Greg's input too, but I would say that the real money, I mean, developing the FPGA, maybe $1 million process, something like that. And whether or not someone else, that is to say that the government or some partner undertakes all part of that, is a question of like, what can we manage to do? Obviously, it's a lot better to the extent that somebody else, comes up with all part of that money. I would say, certainly we have as I mentioned before, we have a proposal in the Air Force to, it's for phase 1, it's a $75,000 proposal. And that's basically to do the kind of groundwork that says, okay, here's what kind of FPGA you need, how much power, how much this, how much that, all those parameters, and early testing on a prototype. And then but to do the rest of the development, maybe $1 million. Will the government put that up? I don't know. Be good if they did, but I just can't tell you. I would say that Greg can speak to this better, but with respect to taking it from the FPGA to in probably a good part of the testing, but also putting it into a production in a chip factory, big money, definitely a round at least. But Greg, do you want to speak to that?
Yeah, when you go from the stage from FPGA to IP block, the design is pretty simple. You do a little bit of layout, but you'll probably want to do some test chips so that you know that you're just always trying to make sure. So you do some test chips and then you test those chips, and that's what costs you money and time. So, then you're talking about needing millions at that point in time. It becomes expensive.
Yep. Right. And can we get a partner to do that? Well, depends,
Yeah, it depends, but that's harder, I think.
Yeah. Right. And this actually speaks to that.
Yeah.
So,
and these are very rough numbers. For example, for development costs, I would say the ASIC IP course probably on the high side if you get really good testing with the FPGA, but still it could be that much. Right. But the unit licensing, this again is a rough idea of what it would cost for a user to get this functionality. Right.
Right. I mean, so again, this is not, like it says up here, it's not a projection. What we're trying to do is give you a frame to how to think about this in terms of, okay, here's the kind of numbers and investment and so forth it takes to get to a point where you have this is really high volume, really big numbers, really where this kind of thing. And if you think about this and you compare it to us to like somebody who's got a new social media thing, it's completely different. We're both in technology, but it's a completely different sort of paradigm in terms of how you think about what you do to make it successful. The economics are different. The amount of investment is different. The way you scale it, everything. There's tons more you'd spend on marketing compared to what we would do, but way less on development, for example. Unless you got to a point where you're really doing super sophisticated stuff, then there's big investments, but it's very different what you're doing.
Yeah. What is also important here, and I've said it before, but I can't emphasize it enough, is the whole development process is very de-risked because at every stage you're working with real customers, solving their real problems, taking feedback, incorporating that into the product. So when you get to the point where you're spending a lot of money on development, you've really determined, again, with a wide set of real customers, that this thing works the way they want it to work. And that really, I think, is important for the business plan.
We have a question here. Once the FPGA has been developed, how much incremental cost is needed for each new application to be customer funded?
Well, maybe I can state this a little bit. The reason to move down this list, to move down these stages, is in general, we don't see a need for customization of the FPGA per customer. So you are solving the same problem, and the only difference in general between the different customers is their data may look a little different. But during the testing and development process, we're going to try to use the widest different types of data we can find to make sure that the algorithms and the FPGA code works on all of them. And this is really important to have a kind of one solution. And when you get to, of course, IP, it's necessary that you've gotten to one solution. You can't change the IP per customer. So this is very different than a customized software model.
Yeah, I would say that probably you would inevitably probably need 2 IP cores because one is building code books and the other's just for runtime or something or some kind of 2 versions of it or something, just because there are lots of circumstances in which you would not be building code books.
Yeah. Or if when we do the design, and this is something that we have to, yet determined, if we can do a superset with some ability to configure that one way or the other, so we don't need to have actually a separate product, but just 2 different configurations of the same product.
So, and this goes to what we were talking about just a moment ago, where do you get the money? And it's really, as I said, the numbers dramatically go up after you get through, you built your FPGA. And this also speaks to, I'm going quick because we're out of time, but this speaks to the kind of the volumes that we're talking about. It's, it's all about that. And the amount of investment you need to make to get to the point where you have the really giant volume. Okay, well, I don't have, we're out of time, but I think that, I hope it was informative today. If there's more questions or anything, please post them and on the Start Engine site. But go ahead, Khalil, you probably have something to say.
Yeah, I just wanted to thank everyone for attending the webinar today. As Charles did mention, we are unfortunately out of time, but I am going to add the Start Engine link in the chat box. So if you do have any questions, please go visit the Start Engine page. There's a lot of valuable information there. We post weekly updates, and there's a whole discussion section there. So if you have a question, please feel free to leave it. Charles is very quick to answering those. But again, yeah, thank you, Charles. Thank you, Greg. And thank you, everyone who attended today. And if you weren't able to attend, this webinar has been recorded. I know there was a question around when will it be posted. Sometime next week, it will be on the Start Engine page. So be on the lookout for that.
Great. Well, thank you very much. Thank you.
Yeah, thank you, everybody.
I appreciate your contributions.
Thank you.
All right.